Hello, my name is Yusuf, and this is my presentation on Heaps. So, to give you a summary as to what I'm going to be going over, first of all, I'm going to be going over the different properties of a weak heap, like essentially what makes a weak heap what it is. Then I'm going to be going over the different operations of a weak heap, um, and explaining how they work. Then I'm going to be doing a runtime comparison between weak heap sort and quick sort, essentially showing you just how much better it is. Then we'll be going over a merging example to show you how to merge two different weak heaps, and then we're gonna be constructing a weak heap ourselves from an existing array. And then lastly, I'm going to be showing you the code that essentially brings it all together. So to go over the properties of a weak heap, first of all, the root has no left subtree. I think that's clear enough. But the other two rules are not so clear, or they're not so they're not. It's easy to misunderstand the other two rules, and I think that's actually what other people get wrong when they read those two rules in the beginning, which is that the value at any node is greater than or equal to the value at any node in its right subtree if it exists. If you don't, if you read this, you might think it's like a heap, but it's actually not because it's only the nodes at the right subtree are less than or equal to the node at the root, in the case of a max heap, of course. Um, um, so this is important. But also, what's also important is that nodes with at most one child only appear at the bottom two levels of the tree, which means that it does not have to be a complete binary tree, as you can see here with this example that I provided you. Nodes C and E, D and F, they're not necessarily they're not necessarily filled from left to right. C or has a null. C's left point C's left child is null, and D's right child is also null. So or more importantly, C's left child is null. So it's not necessarily a complete binary tree. It doesn't have to be. And this relaxation in the restrictions in the structure of a weak heap is what makes a weak heap what it is, because other structures like binary heaps, not only do they have to maintain the heap property across both subtrees, but also they have to make sure that the heap is complete throughout the they have to make sure that the heap is complete, meaning that it's filled from left to right on the bottom level. Now to go over some of the operations, weakheapify. Weakheapify is linear type. GetMin is order 1. ExtractMin is logarithmic. GetGrandparent is logarithmic. And the way GetGrandparent works is essentially a node is a grandparent. A node A is a grandparent of node B if you can get to node B from node A's right son, or by going as far, or by going left from node A's right son. So if you can so B would either have to be node A's right son, or it would be to the left from node A's right son, and that's essentially how you get the grandparent. Now, for merging, merging is simply it's a succinct comparison. It's going to be very clear once I go over the example, but it's very simple. It's just it's a swap if the first node is less than the second node. Merge forest, however, is logarithmic, and it consists of several merges between different weak heaps. And weak heap sort has a runtime of n-1 log n plus 0.086 roughly n. And this is quicksort's runtime at the bottom, as you can see. But it's not immediately obvious which one's really faster. You can't really read this and think to yourself, oh, well, weakheapsort is clearly faster. So I decided to create a little bit of a visual to give a better idea for how just how much faster weakheapsort is compared to quicksort. And you can see here on the top left, these are the two different functions. F of x is quicksort, and g of x is weakheapsort. And the purple region shows the portion in which we keep sort is actually dominated by quicksort, and the grayish portion is the portion in which we keep sort dominates quicksort. So as you can see, up until about 6.3 billion iterations, quicksort happens to be faster than we keep sort. However, once you get to that 6.3 billion iterations, we keep sort actually begins to dominate the runtime. We keep sort begins quicksort begins to dominate the runtime against we keep sort for the remainder of the x-axis. So how does the merge operation work? The way the merge operation works is the new root becomes the larger root amongst the two. So if we take the 5 and the 8, the new root essentially becomes 8. The 5 becomes the right subtree, or essentially the right son of 8, and then and it also keeps its right subtree. However, 8's right subtree becomes 5's left subtree. So the smaller root becomes a right son, but also takes the larger root's right subtree and then has that as its left subtree. I know that's a bit of a mouthful, but I guess to summarize, 8 becomes the new root, 5 becomes 8's right son, and then 8's right subtree, which is the 4, 6, and the 2, becomes 5's left subtree, as shown here. And then this is an example that I'm going to be going over for WeKeep. So the way it works is that we're going to be going from right to left, and we're essentially going to be comparing each node with its grandparents. And I'm also going to be showing and also explaining to you why the reverse bit part is actually so important. So right now we're going to be comparing 6 and 7, because you can get to 6 from 7 by going left from its right son. That's how you know that it's a grandparent. So 6 is not less than 7, so we don't do anything. Now we look at 5 and 2. 5 is actually greater than 2, so we swap them. But however, we also swap 2's subtrees. Since 2 is a leaf node, it doesn't have any. But yeah. Now we're comparing 1 and 4. 1 is not less than 4, so we don't do anything. Now we compare 3 and 7. 3 is not greater than 7, so we don't do anything. 5 is greater than 4, so we swap 5 and 4, and then we swap 4 subtrees. And so the 2 goes on the left, and the 1 goes on the right of 4. And then lastly, we're going to be comparing 7 and 5. And this is actually a good point to show you how the reverse bits work. So essentially, we know up until this point, after performing all this heapify operation, that 7 is actually greater than 3 or greater than 3 and 6. However, since we are swapping 7 with the 5, we don't know the same. We can't say the same thing for 5. We don't know whether 3 and 6, whether 5 is greater than or equal to 3 or 6 as well. And it actually happens to be the case in that in this specific example, 5 is not greater than or equal to the right subtree, because 6 is actually greater than 5. So this is actually exactly why we swap the subtrees, because we can only guarantee that that 5 is greater than or equal to the nodes in the left subtree, but we can't say the same thing for the right subtree. So that's actually exactly why we swap, or why we do that. And the fact that we use reverse bits to do is actually an element of efficiency. But yeah, so yeah, we swap the subtrees. And yeah, this is the heapified WeKeep. This is WeKeepified. This is the code. And that's it. Thanks for watching.